Okay, so we're going to do a few word problems here involving volumes. So this is section 5. So basically we have a lot of formulas, so plugging numbers into formulas is kind of boring, so we're going to try some of these equations. So problem number 52 says, if the height of a right circular cylinder is halved and the diameter is tripled, how is the volume changed? So by what factor does it increase or decrease? So to work these kinds of problems, there's no numbers given, so how do you handle it? Well, if you think about the first thing you do is you write down the equation for the volume of a right circular cylinder, and that is equal to pi r squared times h. And why did I remember that? Because the area of a circle is pi r squared, and if you take that circle and you extend it the distance h, you create a volume. So that's the equation. So what you can do is you can look at it, instead of plugging numbers in, you can look at the ratio of the volumes, because it says how is the volume changed. So what you would do is you'd say, okay, at some initial, the original conditions, the volume is equal to pi r squared h. Okay, so those are our initial things. Then you would say at condition 2, what does it say? It says the height of the right circular cylinder is halved. So I would say, let me put a little subscript here for 1. So that's the radius for the initial case and the height for the initial case. So what it's saying is that the height for the second cylinder is 1/2 the height of the original. So that's what that's saying. The height is halved. It says that the diameter is tripled. So that means that you take the original diameter and you multiply it by 3. Now in the formula we have radius, so if we wanted to see what the ratio of the radii were, is we divide everything by 2. So you'd have d2 is equal to, actually, in this case you're dividing both sides by 2, so it turns out that it's still the same factor. So if the diameter is 3 times the original diameter, and the new radius has to be 3 times the original radius. Okay, so we can use the diameter for information to come up with the relationship between the radii. So at that point, you can say, okay, the volume for the changed volume is going to be pi times r1 squared, r2, pi r2 squared times h2. But then we can use these substitutions. So for r2, I'm going to put in 3 times r1, and then I square it. And for h2, I'm going to put in 1/2 h1. So I've rewritten the heights after the changes have been made in terms of the original values. So what they're looking for is how much larger or smaller is the volume when you make these changes. So what we would do is we would take the ratio of the volumes. That ratio is going to tell me, if it's greater than 1, it's going to tell me that it's larger, and if it's less than 1, it's going to tell me that the volume is smaller. And what I do is I write the volume here in terms of the original dimensions. So I'd have pi times 3r1 squared times 1/2 h1. That's the volume after the changes. And I divide by the volume with the original values in here. And what you'll see is that by doing this ratio, the heights cancel out, but the ratios that I dealt with remains in there. When I square this quantity, you square 3, which is 9, and you square r1, which is r1 squared. So 3r1 squared is 3 squared times r1 squared. And then I divide by what I have in the denominator, and you'll see that I also have the radius squared. So these cancel out as well, and the pi's cancel out. So all I'm left with is 9 times 1/2. Therefore, the volume where the height is halved and the diameter is tripled is 4.5 times the original height. So the ratio, it says here the multiplier is 4.5. So that's how you get that. So even though they haven't given us numbers, by rewriting the dimensions after the change in terms of the original dimensions, we end up, and then taking the ratio of these two volumes, everything cancels out except the scaling factors, where we tripled the radius and halved the height. Okay, so that's kind of how that one works. Okay, 53 says, what is the ratio of the area of the circumscribed square to the area of the inscribed square? So the circumscribed square is the one that's on the outside of the circle, and the inscribed square is the one that's in the center. And you can see that, the four corners of this square are inside, and the the midpoints of the sides correspond for the circumscribed square. So what they want to find is, what is the ratio of the big area to the small area? So how would we do that? Well, what you have to do is think about, we had a problem like this earlier. There's two. The distance from the center of the circle to here is the radius of the circle. But if I draw another line from the center to the circle, that distance is also r. So any straight line from the center to the surface of the circle is the radius of the circle. So you can see that the dimensions of the outside square are going to be 2 times r, because I'm going to have r to here, and I'll have r to there, and you can add those two together. So what we can say is that the length of the sides of the larger square is 2 times r. And therefore, the area of the large square is going to be equal to 2r squared, because of the length of each side. This side is 2r, this length side is 2r. So the area is 2r times 2r, which is 4r squared. And now what we need to do is find the area of the inner circle in terms of r. So in this case, what we have is we actually have this line that goes from the center to the corner of the square, this inside square, is the radius. And if I did the same thing in the other direction, excuse me. So I go this way to the other diagonal. So the diagonal in this case is 2r. So we'll say the length of the diagonal for the smaller square is 2r. So what I need is figure out what is the area based on the fact that this is 2r. Well, to figure out the area of a square, you need to know what the lengths of each side are. So let's draw a version of that square over here to the right. So what we're saying is the distance from here to here is 2r. And what it creates is a triangle. It's a right triangle. And each one of the lengths of each side I'm going to call x. So if I use the Pythagorean theorem for this right triangle here, I'll say that x squared plus x squared is equal to 2r squared. So 2r is the hypotenuse of the triangle, this triangle, and x is the length of the two sides. So what I get is 2x squared is equal to 4r squared. And what I want to do is solve for x, because that'll allow me to calculate the area of this inside square. So we'll divide both sides by 2, so you'll get x is equal to 2r squared, or x squared is equal to 2r squared. Take the square root, and you get x is equal to the square root of 2 times r. So you take the square root of each term in the product. So the square root of 2 is the square root of 2, and the square root of r squared is r. Excuse me. So what I can do is I can say the area for this smaller square is just equal to the square root of 2r squared, because each side has a length x, which is the square root of 2 times r. The square root of 2 squared is 2, and the square root, an r squared is r squared. So if I compare these two areas, let's call this, sorry, this is the circumscribed square, and this is the inscribed square. So if I take the ratio of the circumscribed square to the area of the inscribed square, and this should be r squared down there, I get 4r squared divided by 2r squared, which is just 2. So that's the answer. So the outside square has twice the area of the inside square. It's just using triangles. Actually, I'm not using volumes, but it's recognizing that the inside square, the distance from the center of the circle to the circle, is the diagonal here, whereas for the larger square, it's half the distance between the two sides, and then you go through and calculate the areas. Excuse me. So I slept about an hour last night. I tried to sleep. Yeah. I knew. Well, I went to bed about 10:15. But the New York Times had a really good app for predicting what was going to happen, and they had a little meter showing percentage chance. And so when I went to bed, it was like 58% chance Trump's going to win. And I looked at it an hour later, it was up to like 75%. And I looked at it later, it was like 95%. And I'm going, yeah, the markets actually have been surprisingly stable today. Yeah, they bounced back. So that is encouraging, at least. I'm not sure. I don't think they probably were waiting to see what the U.S. markets were going to do. So they'll probably rebound tomorrow, which okay, this is the last one, I think. In this, no, I actually got a couple more here. So this one says, suppose the diameter of a circle is 8 inches. What is the perimeter of the inscribed square? Actually, this is very similar to the one we just did. What you would do there is you would say that the distance from the center to the circle is 8. It says the diameter of the circle is 8. So if I draw from the center to this corner, which is on the circle, that's 8. So to calculate the perimeter, I need to know the lengths of these 4 sides and add them together. That's what perimeter is. So you can see what I would do. I'm not going to work through the whole thing because it's just very similar to what we just did. This is 8. This would be x, and this would be x. because this is a square, so I know this half of side is going to be the same as half the distance here. So this side equals that side. So what I could do is I could use the Pythagorean theorem like I did here, and I could calculate x. And once I have x, there are going to be 8 x's around this square, because I have 1, 2, 3, 4, each half. This is a half a side. So I have 4 sides, so 8 half sides. So I take whatever this x value is, and I calculate using the Pythagorean theorem like this, and then I multiply it by 8. Okay, this is a little more difficult. It says, in the circle shown with the center O and the radius 6, QTSR is an inscribed square. Okay, so we know what that is because we just did 2 problems. And you can see the square is defined by 4 letters, QTSR. Find the values of P, this is the length of this line segment, PQ squared plus PT squared plus PR squared plus PS squared. So it's basically this length squared plus this length squared plus this length squared plus this length squared. So the question is, how do you figure that one out? Well, because we have stuff squared, it's probably something to do with the Pythagorean theorem. What we need to do is find parts of right triangles that somehow are related to each other. Okay, so it says that the radius is 6. So let's draw a line to represent the radius. So that would be, from here to here would be 6, from there to there would be 6. Actually, to all these different points on the triangle, that's going to be 6 units right there. So no matter where, as long as the point's on the surface of the circle, the distance from the center to there is 6 inches, or 6 units. So I don't remember how to do this, so I'm going to have to think about it for a second. I'm going to take those out for a while. What I'm trying to decide is, are there any right triangles? This is an inscribed square. So I've got to find some right triangles that somehow, so this side and that side, they don't look like they're right angles. But if you take PQ and PS, if you remember back to the previous, one of the previous sections, if you have, this is an inscribed angle, so you go from here to here and from there to there, that angle is half the total angle that's created by those 2 lines. So this, let's see, it's going to be, this angle's 90 degrees right there. And you can do this, so which one was I using? I was using these 2. No, these 2. So if I I'm thinking about this one as well. If you draw from here to here, no, it's these 2. Yeah, it's not coming to me right now. Not enough sleep. So let's just keep thinking about this. I'm proving that some of these problems don't immediately come to you. You have to kind of try a few different things out. Okay, so this is 90 degrees, and because, again, if I drew a line from here to here, it should go through the center of the circle. So that goes through the center. And because that's 180 degrees, this is also 90. Right there. So those are two right triangles. And the two sides are going to be this side squared plus this side squared equals that side squared. And likewise, this side squared plus this side squared is equal to that side squared. I'm trying to think if there's any other triangles that where you'd have other right angles. This would also be a right angle because you have this diameter going through there. So this is 180 degrees, so the inscribed angle is 90 degrees, half 180. And there should be one more. So what I need is this squared plus this squared has to equal that squared. Okay, so I have a right triangle right there. So what I can say is I can say PQ squared plus PS squared equals the hypotenuse squared, which is going to be, I'm just going to say it's D squared. It's the diameter of the triangle. You can also see that, so I've taken care of those two. And then I need PT, which is this, and PR, which is that. So that's the other right triangle, actually. You take this one, again, this, you can draw a line from T to R, goes straight through the middle. So this is 180 degrees. Therefore, the angle, this angle right here, is 90 degrees. And if I take PR, which is this distance, which is one side of the triangle, and this PT, which is the other side of the triangle, the hypotenuse of the triangle is going to be this line right there. So I've got this triangle RPT, with this being a 90-degree angle. So what I find from there is that PR squared plus PT squared, those are the two sides of the triangle, right triangle, is equal to the hypotenuse, but the hypotenuse is the diameter. So what you can see now, see it's starting to come to me, is that if I add both of these, I get the P squared plus PQ squared plus PT squared plus PR squared plus PS squared, so that's all the stuff that's on the left-hand side, is equal to D squared plus D squared. And the diameter is given to the problem as 6. Actually, the radius is 6. So the diameter is going to be 12. So I get 12 squared plus 12 squared, which is 144 plus 144, which is 288. So that was kind of the that was fairly difficult to work through. But hopefully you saw what I was trying to do. I was trying to create right triangles so that I could relate the squares of the sum of the two sides to the third side. And it turned out the third side was something that we knew, which was the diagonal. So anyway. And what I'm going to do is we're going to do this another day because I think you're probably worn out for me doing those examples. So. Okay. Sounds like me. Who's coughing? Okay, so we were talking about translations as using reflections to show translations, that was this part. And we also looked at using reflections to show rotation. I think we did that. Did we talk about that? I think we did. Just in case I didn't. When you do a rotation, so what I'm doing is I'm rotating this figure around this point. And you can see it aligns, and all I'm doing is taking that and sweeping it over to here. The distance from here to here is the same as the distance from there. So everything is equidistant. Each point is equidistant from the center point of rotation. And what we do is we reflect across one line. So this reflects to there across line M, and then you have a second line which is at a given angle, and you reflect across this, and ultimately the net result is you're taking this and just moving it without flipping it and through an angle. So that's what rotation is. And the final transformation you can do is to shrink or stretch things. So this example is kind of like a three-dimensional, well, actually it's not a three-dimensional triangle. What it is a large triangle, and this is the middle of the triangle. Okay, so these dashed lines represent the middle of the triangle. To make a smaller version of the triangle by shrinking it down, you move a certain percentage distance along this line, and a certain distance along this line, and a certain distance along this line, percent-wise, and you create this smaller triangle. So you're just scaling things. You're making, ultimately, we're just changing the length of each side by the same amount. But you can actually do it by this manner. This is where if you have a triangle that has acute angles. So for an acute triangle, you draw these lines. I'm trying to remember what these, I think these lines are if you bisect the angle, here, here, and here, where those three lines, the three bisectors meet, you get a point in the middle. I think this is what it is. Now this is a case of an obtuse triangle. So to scale an obtuse triangle, you take, you have this point M, which is outside the triangle. But we're not going to worry about that. The bottom line is this whole thing, since I'm not testing you on it, is you have these different ways of transforming a figure. You can reflect it across a line. You can translate it, which means you move it left to right or right to left and up and down. And you can create that by doing two reflections across two parallel lines. A rotation around some point, you keep the orientation the same. You just rotate it around at a certain angle, and you can do that by having two non-parallel lines which you reflect across. And I don't know, we didn't talk about this, glide reflection. I think what you do there is you shift it and then you reflect it across the angle. So it's part translation and it's part reflection. And then you can change the size of the triangle by equally changing all the different sides, the lengths. And that's it. Okay, so that's all we're going to talk about that. And the final thing we're going to talk about in Section 9 is Section 7. So there are other topics in geometry that you may not have talked about. Non-Euclidean geometry, topology, and networks. So these are, when you took geometry in high school, you dealt with Euclidean geometry, and that's because Euclid, who was a Greek mathematician and other stuff, came up with these rules, these laws, basically, or postulates and axioms about geometric figures. So let's just read them. So Euclid said, 2 points determine one and only one straight line. So if you put 2 points in space, there's only one line that you can draw between the 2 points. A straight line extends indefinitely far in either direction. And we learned that in Section 1 when we drew the line. There were two arrowheads, and the line goes, it's not just a line segment, but it's a line that goes infinitely long in either direction. A circle may be drawn with any given center and any given radius. All right angles are equal. And given a line K and a point P not on the line, there exists one and only one line through one line M through P that is parallel to K. Let's just see if we can figure out what the heck they're talking about there. So if you drew a line, so here's my line. This is line M. So given, actually it says given line K, let me do that. This is line K. Given a line K and a point P not on the line, there exists one and only one line M. So there's another line somewhere. Actually, let me just clone this thing. So there's another line M through P that is parallel to K. So it's basically saying there's a unique line that's parallel to K that goes through this particular point P. Equal things equal to the same thing are equal to each other. That's one of those, is it commutative, associative? I can never remember. If equals are added to equals, the sums are equals. That's algebra. You know, if you have you know, A plus C is equal to 2, and you have B is equal to 5, these are equal. If you add those, you would get A plus B plus C equals 7. That's kind of what they're saying there. Same thing with subtracting it. Figures that are made to coincide are equal. So what that means is if you have two figures and you can lay them on top of each other, like similar triangles. So if I group those three lines together, or those three things together, and if it says if they're made to coincide, which means that, then they're equal. If you lay them on top of each other and you only see one figure, then they're equal to each other. And the whole is greater than any of the parts. Okay, I'm not sure how you explain that, but anyway, those are Euclid's postulates and axioms, and you can use all these logic proofs to prove all these other theorems that you come up with in geometry. So that's Euclidean geometry. And the thing about Euclidean geometry is that it's also called plane geometry. So it's done on a plane, or it's such that it's a flat surface. So all of those things we learned in geometry apply to flat surfaces, or to probably also to three-dimensional surfaces where you know, 2 dimensions are perpendicular to each other, and the third dimension is perpendicular to the other 2 directions. So all of those things apply to that. But there are other kinds of geometries that are used. So let me just give you an example. So actually the best example is the globe. Okay, the globe is not flat. It's a three-dimensional surface. Pardon me? Oh, heresy. Yeah, right. So, you know, if we try to represent this circle in 2 dimensions, you have this way of drawing maps, and what happens is the things near the North and South Pole become exaggerated in size. And the key thing about this non-Euclidean geometry, which is it's not a plane, it's not a flat surface, it's a round surface, is that lines that are perpendicular in in this geometry are not actually perpendicular in real life. So you can end up with things that are not, they look like they're square, but there's really curvature to them, depending upon how you look at them. That's kind of the basic idea. Okay, that's all I'm going to say about it. And then the last thing I'm going to talk about is this network theory, networks. The classic example is somebody came up with this little challenge, and the challenge had to do with this was some medieval city, and there were 1, 2, 3, 4, 5, 6, 7 bridges, and the question was, could you cross all the bridges without I forget what it was, without traveling the same road twice? Okay. So if you came here, you could go there, and then you would go over there, and then you would go like that, and then you might go like that. And so far I'm doing okay, but if I go this way, I'd have to get back. I'd have to retrace. I'd be retracing my steps at that point. If I went this way to get back over here to do this one, I'd have to retrace my steps. So that was the whole idea. Is there any way to take a path where you don't retrace your steps at any point? And solving problems like that is called network theory. And there's a postulate that says whether it's possible or not. So it says the number of odd vertices on a network, the number of odd vertices on a network is even. What that means is an odd network is where you have 3 lines coming into a point. So this is an odd network or odd vertice, whereas this one would be 1, 2, 3, 4. So there are actually 5. So this is odd as well. This one's odd, but you can come up with ones that are even number of vertices. It says any network with no odd vertices or exactly 2 odd vertices can be traversed. In the case of exactly 2, start at one odd vertice and end at the other. Any network with more than 2 odd vertices cannot be traversed. So if we look at this example, this is odd, this is odd, this is odd because we have 3, 5, 3, 3. So there are at least 4 cases of odd vertices, and therefore because we have more than 2 odd vertices, there's no way to transverse this network of bridges without going back over some existing bridge. Yeah. No, I'm not giving you any homework for those sections. There's no homework for 9.6 or 9.7. Yep. Okay, that's all I'm saying about it. We're done. So on the next test, you will have a few reasonably easy problems to do with volume, surface area, perimeter, and just regular area. But that's the end of Chapter 9. And you only have homework due from the first 5 sections. And I need to plug my computer in here. It's getting low. Yeah, I was thinking about unfriending all my Republican friends, but I decided I shouldn't do that. Even though I have taken Facebook off my phone, mostly because I didn't want to. I needed the space to do something, and I'm just leaving it off. So my wife, Martha, told me later that she gave up on me. She thought I was a bigot or something like that, which I was not doing it from a bigoted standpoint. I was doing it from a voter understanding. And that's, you know, if the only information you get about voting is watching television ads, then you can't make an informed decision. You're stupid. Okay? And maybe I studied too much. I'm overinformed, but you ought to, as a citizen of the United States, you ought to read something about the candidate. So, and until people realize that, we're going to make the same stupid mistakes over again. Up to this point, we've been able to avoid it, but now we have not. We have passed over the I also blame Fox News for this too, because they stoked all this partisan craziness. So hopefully, I don't know. Yeah. Okay, so chapter 5 is a number called number theory, and these are pretty straightforward sections, okay? So you shouldn't have too much problem. Chapter 5 is actually a lot of little tidbits that if you were, again, an elementary school teacher, a middle school teacher, it might be useful to remember how to do this. Remember what these things are. So section 1 talks about what prime numbers are and what composite numbers are. So you probably remember what prime numbers are, but just in case you forgot. But before we do that, before we answer this question, we're going to go back and talk about the different kinds of numbers that we deal with. We talked about this when we were in chapter 3, maybe, different, like rational numbers and irrational numbers. So we're going to talk about this again. So you've got natural or counting numbers, and natural or counting numbers are integers that are positive that you can count on your fingers. Okay, basically, what can I count as a digit? So no negatives. I can't have a negative finger, and you usually don't go 0, 1, 2, 3, 4. You just go 1, 2. You start at 1. So that's what natural or counting numbers are. Then the next step. Okay, so prime numbers are a special kind of natural or counting number. So before we can talk about prime numbers, we have to talk about what it means for something to be divisible by another number. And what divisible means is that when you do the division, there's no remainder. Well, what is the remainder? It's the amount that you would have to add to a number to get, well, let me just use an example. So here's the definition that's in your book. A natural number A is divisible by the natural number B if there exists a natural number K such that A equals B times K. And if that happens, we can say that B divides A. So here's two examples. Here's A. Here's an example of a number A. It's a counting number. And this is another counting number, B. It's greater than 1. It's things you can count on your fingers or toes. So what this says is A is divisible by B if there exists a natural number K such that A equals B times K. So if we put A in there, we would say 12 is equal to 3 times some other natural number. Well, hopefully we'd say, well, 3 times 3 is 9, so that doesn't work out. Let me try the next natural number, which is 4. 3 times 4 is equal to 12. So in this case, for this particular example, K is equal to 4. So there exists a natural number, K, the number 4, such that A is equal to B times another counting number, or natural number. It's kind of a convoluted way of thinking about it. The other way you can think about it from a remainder standpoint, if we take 12 and we divide by 3, if we do that, we end up with a natural number. So one number is divisible by another number if the result is a natural number without a remainder. Because if we took 13 divided by 3, what we would get is 4 with a remainder of 1. So because when I do this operation and I end up with, I know that 4 times 3 equals 12, it's not quite 13, so I have to add additional number somewhere between 1 and 4 to get the final answer. So that's kind of what the remainder is. It's that if I have a number and I divide it, my thing just turned off. Okay, so that's what's divisible. We need to know what divisible is when we talk about prime numbers. Still haven't got the prime numbers yet. Okay. So then the question is, what are factors of a number? Well, the factors of a number are the numbers that multiplied together, the whole numbers or the natural numbers multiplied together that give you the number in question. So when I think about the factors of 30, what I do is I write the numbers down when multiplied together. The natural numbers when multiplied together give me 30. And the way I do this is I start at 1 and end at whatever the number of interest is. And then I start counting by natural numbers. So I'll go to 2, and I'll ask the question, can I divide 30 by 2 and get a natural number? The answer is yes. 30 divided by 2 is 15, so I start from the other direction. So basically, you start with 1 and 30, or whatever the number is you're trying to factor, then you start counting from 1 by 1s, and then you ask the question, can I divide the final number by that number chosen? So I would think in my head, if I put 3 here, can I divide 30 by 3? And the answer is yes, so I'm going to write 30, and I'm going to write the resulting answer, which is 10. And then I'd say, okay, let me try 4. Well, 30 divided by 4 does not give me a whole number, so that I'm not going to put that in there. Then I try the next number, which would be 5. Can I divide 30 by 5? And the answer is yes, and I get 6. And once you get this where they're equal to each other, or they're just one unit difference, then I'm finished. And then I have reached my list of factors of 30 by starting at the edges and working my way in, and then just checking the count. So that's what factors are. So I think I've got an example. We'll just give you an example. Let's give you one for you guys to work on. So let's say I had 27. So what are the factors of 27? So again, in an organized fashion, rather than just kind of thinking about it, which numbers can I divide 27 by and get a number without a remainder, the best thing to do is to start off with the two numbers, 1 and 27. And then I go to 2, and I say, well, I can't divide 27 by 2 because it's an even, I'm dividing an odd number by an even number. That's not going to work. So then I go to 3, and I say, okay, 3, yes, I can divide 27 by 3, and that's 9. And you can try 4, but that's not going to work. 5 is not going to work. 6 is not going to work. And when you get about halfway in between, you say, I'm done. So the factors of 27 are just 1, 3, 9, and 27. What does that mean? It means I can divide 27 by 27 and get a number, which is 1. I can divide 27 by 9 and get 3, which is a number. I can divide 27 by 3 and I get 9, which is a number. And I can divide 27 by 1, which is 27, and that's a number. So those are all, this is divisible by each one of these numbers. That's what factors are. It's a list of the numbers that an original number is divisible by without a remainder. The word multiple. What does multiple mean? Well, multiples, you start with the number of interest, 6, and you just multiply it by correspondingly larger natural numbers. So 6 times 1 is 6, 6 times 2 is 12, 6 times 3 is 18, 6 times 4 is 24, etc., etc. We can draw little dots there. So that's what multiple means. And again, you can see that each one of these numbers is divisible by 6, and you get a number. 30 divided by 6 is 5, 24 divided by 6 is 4, 18 divided by 6 is 3. So that's what we mean if somebody asks you for multiples of a number. So the multiples of 3, you would take 3 times 1, 3 times 2, 3 times 3, 4 times 3, 5 times 3. These are all multiples of 3.
Okay, for your discussion board assignment for this lecture is I want you to do the factorization. So what is the factorization of, let's think of something here, 42. So I want you to list all the factors of 42. So 1 and 42, and then the other ones that are in between. So if you can enter that, I'd appreciate it.
Okay. Here's one more example. What happens if you have a case where you look at trying to figure out what numbers can be divided by, 25 can be divided by, and give you natural numbers. Again, we would do 1 and 25. We can't divide it by 2. We can't divide it by 3. We can't divide it by 4. Yes, we can divide it by 5. But you might be tempted to include 5 twice because 5 times 5 is 25. So isn't 5 and 5 again factors of 25? But you only list the factors one time. So anytime you have a perfect square root of something where you just have this times itself gives you the answer, you just list it one time. So that's what, is there more than one? Meaning, is there more than one 5 to list? And the answer is no. Because the reason you say that is 1 times 25 is 25. 5 times, well, I don't have anything to multiply it by. But that's really not what we're looking at. We're asking the question, what numbers can I divide 25 by and get natural numbers? Well, 25 divided by 25 is 1. 25 divided by 5 is 5. 25 divided by 1 is 25. So don't include I'm going to skip that. Skip. Okay. So here are a couple of other examples of factors. So again, you would list 1 and 20 to start with. Then you'd ask, can I divide 20 by 2? The answer would be yes. So I put 2, and the resulting number, 20 divided by 2, is 10. Then I go, can I divide 20 by 3? The answer is no. Can I divide 20 by 4? The answer is yes. The result is 5. So by doing this dividing thing, coming this way, I get 2 factors at one time. I could just ask the questions, what numbers can I divide 20 by and get a natural number, and I could just start guessing. But by going in this ordered approach, I get 1 plus the second one for free. And likewise here, when I chose 4, I got 5 automatically because I knew these 2 multiplied together had to give me 20. And then a number that gives you a lot of factors is 72. So again, I list 1 and 72. And then I try the next larger number, which is 2. Can I divide 72 by 2? Yes. That gives me 36. Can I divide 72 by 3? Yes. That gives me 24. Then I try 4. Can I divide 72 by 4? Yes. That gives me 18. 5. You can't divide 72 by 5 because it doesn't end in a 0 or 5. And then I try 6. Can I divide 72 by 6? Yes. The answer is 12. 7's not going to work. I go to 8. 72 divided by 8 is 9. And you can see, right, there's no more numbers in between, so I'm done. And I get my entire list of factors. So that's the way I would suggest you do it. Instead of thinking, well, can I divide this by 16? Let me try it, plug it in my calculator. Oh, can I do it by 18, let me pull out my calculator. Doing this way is going to give you all the answers much more easily. Okay, so why all this stuff about factors? Well, because the definition of prime numbers has to do with factors. So you got to know what factors are before you can do it. So the definition of prime numbers is a prime number is a natural number greater than 1 that has only itself and 1 as factors. So that's what a prime number is called. If it's not a prime number, we call it a composite number, because that means that there are two other numbers that can be multiplied together to get that result. If there's only 1 and that number, then it's a prime number. So let's just do an example. So if I looked at 6, and hopefully you realize that's not a prime number, but let's use the definition. It says a prime number is a natural number greater than 1 that has only itself and 1 as factors. So I have to list the factors. So I'd list 1 and 6, and then I go to the next larger number, which is 2. Can I divide 6 by 2? Yes, the answer is 3. So I have more than just one pair. I have more than just 1 and 6. So therefore, this is composite because it has more than one natural number greater than 1 that, well, it has, it's not prime. Okay, so if it's not prime, it's composite. So because it's not prime, because I have more than just the factors of 1 in the number. Whereas if you think about 7, you'd say, okay, well, I'm going to start off my two factors of 7. I'm going to start off with a 1 and 7, and then you try other numbers. Can you divide 7 by 2? No. Can you divide 7 by 3? No. And can you divide 7 by 4? No. So all that's no. So I only have two factors, 1 and itself. And because of that, this is a prime number. Now, how many people think if I showed them a number from 1 to 100, they could tell me whether it's prime or not? You ever did that in class? Do you ever remembering that or think that was important? So I'm going to quiz you guys on this. And let me do it by making up a spreadsheet. And I'm going to share this. So what I'm going to do is make up a spreadsheet with numbers from 1 to 100 and be prepared. So I'm just going to go around. You're going to say yes or no, okay? We'll see if you're right or not. You don't like this? Put you on the spot, huh? Okay, well, 1's not a prime. 1's never a prime number. What I'll do is I'll put a little red thing when it's a prime number. Or when it's a prime number. I didn't mean to do that. So let me try that again. Okay. So 1 is not a prime number. So I'm going to put a little red there. Is 2 a prime number? Yes. Yeah, it's the only even prime number. Alicia, 3. Is it a prime number? Yes. Okay. So, actually, I should take that one off. That wasn't a prime number. Yeah, so 3 is a prime number. Okay. 4. Laramie. No. Yes. Okay. Now I can't see it. There it is. Okay. Harley. 6. No. Okay. Hold on here a second. I'm having a problem with Mr. Webb's first handle. Huh? Oh, I forgot Caitlin. Yeah. 7. Prime. Yep. Okay. Justin. There it came to me. 8. Is that a prime number? No. Okay. Jackson. 9. No. Mary Jo. No. Okay. 11. Yes. Okay. 12. No. 13. Yeah. Yeah. It's a prime number. Okay. 14. 15. Caitlin. It is prime. Okay. 15 divided by 3 is 5. Okay. And actually, we can pretty much, all the even numbers above 2 are not going to be prime numbers. Okay. So let's just do the odd ones. Yeah. Anything that ends in 5 and 0. And that's actually, so, you know, I'm going to tell you which ones they are just because I remember. So 17 is a prime, 19 is a prime, 23 is a prime, 29 is a prime, 31, 37, 43, 47, I think 53, 59. Anyway, after a while you get used to them just because you might remember in a multiplication table. 61 is a prime number. 71, I don't think it is. So the way you can go through here and figure out what the prime numbers are kind of like what James was talking about. What we can do is we can take all these things off, and I'm going to highlight numbers. We know 2 is a prime number, but every other even number is not a prime. So I'm going to put the red on those, so we can go through here and basically fill in all of the ones that are even. So those are all not primes. Okay. Now, the next thing you do is you think about multiples of 3 instead of multiples of 2. So if you do that, you're going to get 9, 12, 15. Well, actually, yeah. Another thing we can do, before we even do that though, after 5, all of these are not prime numbers because they're all divisible by 5, and all of these have already been taken care of. Okay, so now we go back to multiples of 3, and we can go ahead and fill those in. 24, 27, 30, 33. So what I'm doing here is multiples of 3. So we're talking about multiples. 39, 42, 45, 48, 51, 54, 57, 60, 63, 66, 69, 69, 72, 75, 78, 81, 84, 87, 90, 93, and 96, and 99. So those are all multiples of 3. So I get rid of those. We've already done 4 because we've already done 2. So we'll have to do it again. We've already gotten all the multiples of 4. So then we've done 5, 6, 7. So then we do multiples of 7. So we have 7, 14, 21, 28, 35, 42, 49, 49, 56, 63, 70, 77, 7 is, oh, yeah, I need to take that off of there, thank you. So we shouldn't include 7. All multiples of 7 except for 7. 77, 84. What I'm doing is just adding 7 to each number. And we got that. 8 we've already got with 2. 9 we've already got with 3. And we're done. So what I've done is this is called the sieve of Eratosthenes, and it's a way of coming up with all the prime numbers between 1 and 100 by first getting rid of all the even numbers, then getting rid of 5s and 0s as a second digit, so multiples of 5 or 10, and then we went to, what was the next one? 7, 3. We did multiples of 3, so it's all the numbers between 0 and 10, or 1 and 10, and we've eliminated all these, so these are all the prime numbers now. So it's 11, 13, 17, 19, 23, 29, 31, 37, 41, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, 97. So those are all the prime numbers between 1 and 100. There's an interesting thing here about some prime numbers is, you know, you can go for a long distance without getting a prime number, and then you have ones that are only 2 apart. So 59 and 61 are only 2 apart. Whereas we go to here, we've got a space of 5, and then we have a space of 1, 2, 3, 4. But then we have here the 2 are next to each other. They have a special name, and I think it's in my notes. But you can go out to prime numbers out to a million. And there are still numbers, even with 5 or 6 digits, well, to infinite number of digits, and you'll end up ones where they're only 2 apart, just kind of randomly. There's no way to predict that they are or aren't going to have those characteristics. Okay, so that's it for today.